Hey guys, volume of spheres for geometry. The essential question, how can you use the formula for the volume of a sphere to calculate the volume of composite figures? Well, spheres exist in the real world, and we use them everywhere. If you don't believe me, name a sport, name 5 of them, and see how many of them actually have a round or spherical object involved. Alright, so our answer in simplest terms is you break the figures into familiar figures, so piece by piece, including spheres and hemispheres. The ones that we know the formulas for. So we break them apart and find out what the formulas for each part is, and then we combine those individual volumes together, okay? So, developing the volume formula for a sphere actually comes from these two concepts. So let me try to explain this in simplest of terms. Now, the way the book explained it was pretty wordy, pretty lengthy, and not very fascinating. So one of the ways that I decided to do this was showing you first this picture on the left. And if you were to actually take a hemisphere is half of a sphere, okay, and fill it full of water, and you poured it into a cylinder with the same radius, okay, so their R's are the same, okay, you will actually fill up the container exactly at 2/3 of its volume, okay, if you filled up the cylinder. So you'd be at 2/3. See, you have that 1/3 here plus the other third, 2/3. Now that's just half of a sphere that we poured in, right? Now, if you think about it, by this GIF right here, let me see if I can get the drawing to go on top of it. If you notice how the cone is pushing into the cylinder, and yesterday we did learn that a cone was 1/3 of the actual cylinder. So if you remember that, that means today we're talking about the other 2/3 of the cylinder, the empty spot of it. And that empty spot actually goes and belongs to the hemisphere, or half of that sphere. Okay, so that's actually, you know, the half is glass, or the glass is half empty, the glass is half full. Well, in this case, the glass, well, yesterday with cones, the glass was 1/3 full. But with spheres, well, now it's 2/3 full. Okay, so that 2/3 that was empty was actually the sphere just kind of coughing in the background from yesterday's lesson. Okay, so let me see if I can go at this a little bit more in detail with the formula now. Now, developing the formula of a sphere. Now, we have our sphere. This is going to be the worst drawing probably ever. Bear with me. And we have this going on here, and we have, so I'm just kind of showing you a sphere drawn, of course, by hand. Now, with the sphere, we have the hemisphere, and the hemisphere basically is just half of a circle, or sphere, I'm sorry. That was a terrible, terrible, terrible drawing. And we have a radius, right? And we have another radius going across this way, right? Well, we also have a radius going this way. So I said that the volume of a hemisphere is 2/3 of a cylinder. Now, a cylinder is pi r squared times height, but with hemispheres, your height is actually your r. So instead of h, it's another r. So there's actually 3 r's. There's one here, and there's one up there. So you have 3 r's. Now that's just a hemisphere. That's half of a sphere. So if you were to get a full hemisphere going on here, you would have to multiply this whole thing by 2. So 2 times 2 is 4, and that's over 1/3 still, pi r cubed, which is basically the formula for a sphere. So again, this guy right here is the thing to know. All right, so example 1, finding the volume of a composite figure. We have a hemisphere attached to a cone. So let's go ahead and find the volume of the hemisphere. Okay, a hemisphere, again, is half of a sphere. So you can always do 1/2 of 4/3 pi r squared. What's our r? Or not squared, I'm sorry, cubed. Our r looks to be 5. So 5 cubed. Okay, so we'll find that. And you should get 5 to the 3rd power. Your calculator does a lot of the legwork for you. Times, and those 4 gets reduced down to a 2. Times 2 divided by, actually let's do this, 5 to the 3, it's 125, times pi equals that, times 2, and then divide by 3. So we get, for our volume here, 261, they say round to the nearest cubic centimeter, so 262, okay, cubic centimeters. Okay, so we found the hemisphere. Now we got to figure out the cone. Now the cone does not give you the actual height, it only gives you the slant height. Okay, so we actually have to use Pythagorean to find the missing piece. Okay, so we have 5 squared, and our hypotenuse is the 13 centimeters. 5 squared is 25. 13 squared is 169. Okay, now we have to subtract the 25 from the 69. We get 144. And that's working out terribly with my touchscreen. There we go, 144. How do you get rid of the h squared, or the square part, square root? And you should get 12. Of course, there's a plus and minus 12, but negative 12 doesn't quite work for distance or length, so it has to be the positive 12 centimeters. So we found the height. Awesome. Now we can actually use the equation. So our radius, again, for our hemisphere is the same radius as the cone because they're basically just right on top of each other, right? So your radius has to be 5. Our formula is as thus. So radius is 5. Our height we found out to be 12. So we have 12 times 5 squared, which is 25, which is 300. And you could do 300 times pi, and then divide by 3. And you get 314 cubic centimeters. But that's not the final answer. The final answer is combining the hemisphere and the cone. So 314 plus 262, total volume equals 576 centimeters cubed, or cubic centimeters in real life. That's how we say it. So that is your actual answer. Okay, so your turn. You can work with someone on this. You have a hemisphere, okay, and it's carved out of a cylinder. So I'll go ahead and get you started. First things first, they don't give you the radius, do they? But they do give you a diameter. Okay, so what do we know about the relationship between a diameter and a radius? Okay, that's what you have to ask yourself to find your R. And then basically, again, the hemisphere is being carved out of the cylinder. Okay, the hemisphere is tangent to the base of the cylinder. That means they're literally just touching flat on there. Okay, so we know that their radiuses for sure are the same. So find the volume of the figure to the nearest tenth. So again, the volume of the cylinder minus the volume of the hemisphere. And look back at your notes, and you'll find the formula for the hemisphere. If you want, you can just do 1/2 times the volume of a sphere. Either way, it'll get you your answer. Make sure you round to the nearest tenth, and your answer is definitely going to be in a cubic inches. All right, buddy time. I want you to find the expression for the volume of a cylinder with the cone removed. So take the volume equation for a cylinder, subtract by the volume of the cone. And you're going to get some expression to represent that situation. So go ahead and try it. Combine like terms, okay, and guess what? You've seen something pretty much like that. So again, look back at your notes, and it'll give you a good idea of where you're going. There's your homework. If you have any questions, let me know. Good luck.